we don't bite, right? Okay, cool. Let's get started. Welcome to section 1, 2, 3, 6 out of 10. Okay, that's pretty good. Yes, question? Hi. All right. Yeah, welcome to section. So today is National Slurpee Day. Happy National Slurpee Day. That's not the holiday Tyler was mentioning, but might as well be. Okay. All right. Some announcements. Assignment 1 feedback was released like a couple days ago. Take a look at Paperless, and if you have questions, let me know. Okay. Assignment 2 was due yesterday, and I'll release feedback. The official deadline is next Wednesday. I try to do them a little bit earlier, so you'll probably get them back Sunday, maybe Monday. Okay. If you have questions, email me. Email me. Assignment 3 is due next Wednesday, I think. Is it Wednesday or Thursday? Wednesday, right? I think it's Wednesday. Okay. There are 2 parts to it. Make sure you read the spec very carefully because it sometimes forbids you from using certain features. Okay. I think one of them says you can't use any loops, so make sure you don't use any loops. Okay. Finally, I said this week is the most important week, and that's true for lecture. For section, next week is probably the most important section. So make sure you come next week. We will tackle a lot of like very classic CS problems. So make sure you come next week, okay? It's really, next week's my 3rd favorite section out of 8. Okay, if you're the 1230 or 130 section, make sure you submit all files, including extensions, within one submission, okay? Because it's easier for me to comment if you do that. Yeah, and if there's anything you want me to note specifically about your submission, put it in the header comments. That assumes that you have header comments, okay? Cool. This is just a quick thing I just wanted to briefly mention, but style is important. If you're interested, go look up this case, Bookout versus Toyota. This is really interesting. Toyota got sued because their code was really bad, and that caused a fatal crash with one of their cars. Okay, so some of the reasons they identified as potential reasons for why the car crashed. Here are some of these, and you actually know most of these. Okay, so even though we tell you like style is important, remember that if you ever go into the real world and have like an engineering job, remember that what the code you write does impact lives. So maintaining good style with your code is very important. Okay, just want to briefly mention that. If you're interested, go look up that case. That case is really interesting. Okay, cool. Otherwise, let's get started with recursion. Today we're going to go over, we're going to start with a recursion trace. So we're going to do the same thing as we did last week with the animations. And then we'll talk about a couple examples. So the first example, stutter stack, it's a really informative example, although it's a little simple compared to what you'll probably see on the assignment or the exams. So later we'll do 2 more examples. One's called digit sum, which is something you probably would see on an exam. The last question is called evaluate, and that's really cool. Okay, so we'll write a parser, which is, for example, if you typed in something like this, what you see on the whiteboard right now, into Excel, it would like evaluate it for you, right? Now you might wonder, okay, how do you like parse this? This whole thing is a string. How do you parse this? Well, you can use recursion to do that. Okay, so that's something that we'll be doing. Okay, let's start with the recursion trace. Okay, so take a look at question 2. I really like this recursion trace question because it shows one of the most common mistakes on the exam. Okay, so start by looking at, on this handout they named it mystery B, but look at mystery B, and we're going to do 3, 4, parameters 3, 4. Okay. Yeah, so the purpose of these questions is really to just, okay, here's a function call, trace through what happens, tell me what it prints out. Okay, and something I really like to do in these examples is let's go around the room and we'll go like step by step, try to figure out like what is done at each step. If you're not sure, feel free to pass, and we can discuss what is happening at each step. Okay, is that okay? Is that okay? All right, let's get started. Okay. Also, these slides look really nice, so I spent a lot of time on these. Please enjoy them. All right. So this is the code, and we passed in the parameters x equals 3 and y equals 4. Okay. Down here, you see this thing called the call stack. If you ever debugged in Qt Creator, this is probably going to be important for this assignment, where if you ever want to like try to jump between different recursive frames, you can see what the call stack is to see like what the recursive calls are being made. Okay, and that's the console over there. All right, can we start over here? Okay, so yeah, don't be nervous. We're just going to go around the room. If you're not sure, feel free to pass. Okay, so what happens here?
So it doesn't go into the if y equals plus 1,
Mm-hmm. Yeah.
1. And so then it goes into this, and prints out 3 times 4, so 12.
Great. Yeah, so we don't do the base case. We go into the recursive case, and we print out 3 times 4. Okay. Don't forget that comma as well. Cool. Next, so what happens when we reach this line? Do you want to? Let's do. Yeah, let's go. You first.
So you're going back into like mystery 12 at the top with, is the x now 12?
Yeah, so the x now, so we pass in the x, and we also pass in y minus 1. Yeah.
So 12 and 3.
Yeah. I don't think x is 12 here. Yeah. So don't. Yeah, it's still 3 because yeah, when you do x times y, we haven't actually changed x.
Okay, so
Yeah.
3
Mm-hmm, yeah. Yeah. So when this happens, we're actually creating a separate stack frame. It's the same copy of the function, but remember when we come here, we have different parameters. Okay, awesome. Let's go next. Do I start with you? Yeah. What happens next?
So it's y is not 1, so it goes to else statement. And we output 3 times 3 and a comma.
Great. So that's 9.
Yeah. And then we call the next recursion function and create another.
Sure. Okay. What parameters are passed in?
It's like 3, 2.
3, 2. Yeah, exactly. Okay. So we pass in the parameters 3 and 2. Okay. Cool. Let's go next. So what happens next? Let's start with you. Yeah.
The same thing again. It does not go into that one because y is not equal to 1.
Okay.
So then it prints out 3 times 2 is 6 comma, and then it goes to the next recursion with an input of 3 and 1.
Sure. Okay. So yeah. So we print in this example, x is 3 and y is 2. So we pass in the parameters 3 and 1. Okay. Cool. Let's go to the next recursive frame.
This one y equals 1, so you're going to output 3 and end that call.
Okay, great. So here we print, we reach the base case. So we print out 3. And then because this is an if-else statement, we just skip everything else. Okay? Now, this is where a lot of students make a mistake where they're like, okay, I reached the base case. I'm done. Right? Yes?
It would print the counting for all the other mysteries that have been called in the recursion.
Yeah, this is really important, where when you are done with the base case, make sure you go back to where the recursive calls were being called. Okay? This is kind of similar to when you, like in Game of Life, for example, when you decomposed and you called other functions. When you call another function, the control flow goes to that function and it runs that function. But when it's done running that function, the control flow goes back to where you called that function and it keeps going. Okay, so just because you reached the base case does not mean you're done. Right? You have to go back to where that recursive call was called, and you have to continue. Right? Notice that there are more cout statements. Okay, so what happens next? Let's just continue with you. Yeah. So what happens here? What is printed?
Would it print 6 or?
Yeah, it'll print 6. So it'll print a comma, and then x times y here is 3 times 2 is 6. Yeah, so you're exactly right. We print comma 6.
Let's do 9 and 12.
Yeah, okay. Since you mentioned that, let's just quickly go through it. So here, we finish the function. So the stack frame is gone. And then now we go back to what recursive call happened to create that stack frame. Well, we go back to here, and then we print the comma x times y. Notice that here, x times y is 9 because the x and the y here are 3 and 3. Okay. The key thing to note is in every stack frame, the local variables you have, x and y, they are separate. Right? So they do not interact with each other. Okay, so here we print out x times y, that's 9. And then if we come back out here, what's printed out here? 12, yeah. Okay, and then we're done. All right. Try parts 1 and 2 on your own time, definitely before the midterm. On the exam, you'll usually see something like 3 recursive calls. The first one is like a really straightforward base case, and then the other ones are more complicated. Okay. Now, here's a common mistake, and that's exactly the mistake that we were just talking about, where you're like, okay, we reached the base case. So I print 3 here, and then since I reached the base case, I'm done. So I'm like, okay, everything's gone, I'm done, and that's wrong. Okay. The most common wrong answer on this question is that you see down there, because you forgot to go back to all the other recursive calls. Okay. For example, here, this is initially when we said x equals 3, y equals 4. Right? This made a recursive call to this other stack frame, x equals 3, y equals 3. On an exam, when you're tracing this, I highly suggest you draw these out and make sure you draw these colored arrows that you see up here, right? The red arrow saying where the recursive call is being called, and then the blue arrow reminding yourself that when the function is done, make sure you go back to that calling function. Okay, so if we repeat this, you see, okay, we make another recursive call here, we make another recursive call here. When we finally reach the base case, remember to go back to these blue arrows, make sure you go back to where you left off, and to print whatever is after the recursive call. Okay, does that make sense? Right, any questions? All right, just a little story. When I took this class a couple years ago, on the midterm, our professor gave us a recursion trace problem, which had you trace like 30 different stacks. Yeah, so it was like that, but like 30 different levels. So that was a pretty fun question. It took me 15 minutes to do it once, and then I spent another 15 minutes trying to make sure I got the right answer. I got 2 different answers, so I gave up on that question. I was probably doing it wrong, but yeah, I don't think Tyler will be that mean. Question, yes?
Where'd you get on that test? If you don't mind me asking?
I'll tell you off video. Yes, I'll tell you off video. All right. Any other questions? Cool. Okay, so let's do an example called stutter stack. This is a pretty, it's a little bit simplistic in that no one actually writes this as a recursive function, but it's also like a really informative example, so I kind of want to go through it, okay? Something I want to talk about recursion is that it's okay if you don't understand recursion the very first time you see it, but and our goal is we want to try to explain it in as many different ways as possible. So I'm going to try to explain it in a slightly different way than Tyler would have explained it. Hopefully, at least one of them vibes with you, okay? Cool. Okay, so the question we want to write, this is the stutter stack example from, I think it's question 4, question 5. All right, so you can read it, but I'll quickly explain what the function wants you to do. So we want to write a recursive function named stutter stack that accepts a reference to a stack of integers. So you can see over there the ampersand as a parameter and replaces every value in the stack with 2 occurrences of that value. Okay, so just as a visual, this stack that you see over there, it has 28, -2, 1, -7, 5. By the way, these colors are from the slides I used last week, if you remember the reds and greens. And we want to essentially stutter stack this stack. Okay, what would it look like if you replaced all occurrences with 2 occurrences of that same one? Yeah?
It would just be 28. Well, what we want to do is 28, 28, -2, -2, 1, 1, -7. So
Yeah. Yeah, exactly. So we take this one and we replace each occurrence with twice of that. Okay? Any questions? Okay. Now, before we start writing any pseudocode, I want to explain 3 recursive strategies that I personally like to use to think about this question. Okay? So do you remember, I think Tyler mentioned this in class, which is when you want to write a recursive function, you assume that you have access to that function itself. Did Tyler say that? Probably something like that. So the idea is because you're writing a recursive function, you can assume that you can call your own function itself, right? Now, I personally find that really confusing. Like, isn't that the function we're trying to write? Why can you call it? So how I like to think about this, and this was inspired by, anyone remember Fruit Ninja? Okay, Fruit Ninja, right? So it was like 10 years ago. I was super addicted to it. Something you'll notice from like apps like that is like they offer you like a light version, which is like you have to, you can only do like 10 levels or so, but then you have to pay to get the access to the other levels. Yeah. So instead of assuming you have access to like your own function, assume you have access to a light version of the function. This function is completely functional. It does everything you want it to do, but the only difference, just like a light version of Fruit Ninja, is that you have to. It only accepts inputs that are smaller than s. Okay. So for example, before our input accepted like stacks of size 5, right? Suppose this function stutterstack light only accepts inputs smaller than 5. Okay, so suppose you were given this stack and I called stutter stack light. You would get the same thing but stutter stacked. Okay. What if you tried this one? Get the same thing, stutter stacked. Okay. What if you tried this one? Yeah. Yeah, exactly. But be careful because stutter stack light, because it's the light version, you're only allowed to accept input smaller than the original one we had, which was like 5. Right. So here, if you try to give it like a stack of size 5, it would not work. Okay, because the light input has to be smaller than the original input. Okay. What if you tried this one? Stack of size 6. Yeah. Okay. It would not work. All right. Any questions? All right. Cool. So yeah, one weird edge case to think about is what happens when you call stutter stack light on the empty stack. It should just not do anything, right? You're technically just stutter stacking nothing. Okay. Cool. All right. So yeah, so that's like our first recursive strategy. Assume you have access to this function. Okay. How I like to approach these questions is we're going to kind of see this like a puzzle. All right. My analogy is suppose you didn't want to pay for Fruit Ninja Pro or something, so you instead you had to write your own Fruit Ninja, given that you have access to Fruit Ninja Lite. The question is, can we write stutter stack only using stutter stack Lite and doing as little work as we can? Okay. Now, before we get to that, let's look at a second recursive strategy, and that is to be short-sighted. You might wonder what that means. It means pretend that you can't see beyond the first thing in your parameter. Right? So what we're going to do here is, instead of looking at this stack, we're going to pretend we can't see anything beyond the very first element. Okay? Now, you don't know how many of these gray ones there are. There could be one, there could be many, there could be none. Okay? We can't see that far. And that's kind of the point of a stack, right? You can't see beyond the very first one. Okay? When you do all recursion problems, pretend you can't see beyond that first one. Okay? But the thing you do know is you do know that there are fewer of these than in the original input, right? Because you took one off. So it has to be fewer of these. Now the question is, if we just removed the top, this input is smaller, right? What can we do with this smaller input? Yeah, the light function. Because we made our input smaller, we could just stutter stack this smaller function because our light version can handle that. Right? So one way around this obstacle, because we don't even know how many elements are in here, but we can use stutter stack light. Okay, let's imagine how you would do this. So if I wanted to stutter stack this entire stack, how could you use stutter stack light? Yeah.
We can just pop the first element
Okay.
and pass the rest of the stack to the shutter stack light.
Sure. Okay. So we pass this stack into stutter stack light. We can do that because this stack is smaller than our original stack, right? Okay. So if you call stutter stack light, you can assume it works perfectly, and then it does something like that. Now you have no idea how it does it, and here's the beauty of recursion: you don't have to think too much about how it's doing it. Yes, that's exactly my stack. And then what's left to do after that?
Put it back twice.
Put it back twice. Yeah. So 1, 2. And that's how you stutter stack a stack using stutter stack light. Any questions? Ignore that. I'm sure it's not catching you on video. Okay. This almost always works except one case. Can you think of when this procedure won't work? Yeah, empty stack, right? Because we have to pop a stack. We have to pop from the stack to be able to use that stutter stack light. But if you have an empty stack, you can't do anything, right? In which case, what should you do? I kind of gave away the answer.
Nothing.
Yeah, do nothing, because if you try to call stutter stack on this stack, it should do nothing. You should get that empty stack back, right? So in that case, do nothing. Okay. Now let's go back to some pseudocode. So suppose we wanted to write the function stutter stack. How would you use stutter stack light? So here we first pop the top element, which we call k, off. What's next?
We judge whether the stack is empty.
Okay, judge if the stack is empty. Now, does it matter if the stack is empty or if it's not empty?
Yes, because if it's empty, you can pop the top element.
True, yeah, true. So in that case, we'd write a separate case for that, right? Okay. You'll notice this blank space we see up here.
Yeah.
That will be the base case there, okay? But here, we don't have to check if our stack is empty, right? We can just assume, we can just call stutter stack light, and that would work, right? That would stutter stack the stack except the top element. And then how do you finish the function? So we've stutter stacked that smaller stack. Yeah?
But then, like you pushed it last, you popped off twice.
Yeah, exactly. So we just pushed k back in twice. Okay. Now going back to the example of what you mentioned, this almost always works, and the other special case is when the stack is empty. In which case, what should you do? Do nothing. Yeah. So literally do nothing. Now, okay, we call this the base case, and we call this the recursive case. Okay. Let's quickly think about how you would think of like what the base case is. Okay. Some people say there are two different ways you can like call what a base case is. One is when you can't make the input any smaller, right? So in this example, our stutter stack light, we can always use stutter stack light to make our function stutter stack. The only case it can't do that is when the stack is empty, because then that means you can't pop anything from it. Okay. Other people like to explain it as when it's trivial to solve. Stutter stack of an empty stack is pretty simple. Do nothing. Okay. So here, if S is empty, don't do anything. When you do problems like these, you'll often see like these very common base cases. If it's an int, you can probably guess it's probably going to be 0, string, probably an empty string, ADTs, an empty ADT like this one. Next week we'll get to pointers, and you'll see probably null pointers. Okay. Now you might be wondering, okay, so I know that we can use this stutter stack, but what exactly does a smaller input mean? Right, smaller is in quotes. So what does that actually mean? Any guesses?
Means you will eventually get to the base case.
Yeah, exactly. Okay, so smaller in this example, usually smaller intuitively does mean smaller. So in our stutter stack, smaller literally means fewer elements. Okay, technically, you want to move like forward progress towards a base case. The goal is if you keep making these recursive functions, you'll eventually end up at a base case. Okay, let's go through some like examples you did in class. All right, remember factorial? Right, in factorial, when you kept making these recursive calls, you went from 4 to 3 to 2 to 1, and then eventually reached 0. Okay, the idea of forward progress is we want to eventually move slowly and slowly towards the base case. Okay, how about palindrome? Palindrome, you started removing characters, and you would slowly, gradually move towards the empty string. Okay. How about our current function? Well, if you kept tracing the recursive calls, the stack would get shorter and shorter and shorter until it reaches the base case. Does that make sense? Any questions so far? Okay. If you took CS 106A, you'll know this odd example called hailstone. Is anyone in CS 106A right now? Okay, there's this example called hailstone, which is, there's this thing called the hailstone sequence. You can write this recursively, and one odd thing you'll note is the numbers sometimes go down and up. This is just an odd base case, but basically the idea is forward progress means you're moving closer and closer towards the final base case. Okay, What happens if you don't move in forward progress? If your input's not smaller, what happens? If you try to call like the function recursively. Stack Overflow, yeah, because the function's just gonna keep recursively calling itself. It's never gonna get to a base case. Eventually, your stack frame fills up and you can't do that anymore. Okay, cool. Some tips. When you are figuring out the base case, you should try to think about this diagram, right? How is the recursive call going forwards? Okay, but when you're writing the recursive case, don't think too far ahead. Be nearsighted. Only think about that one step, that one little work you have to do. Okay, and that's our pseudocode over there. Okay, now when we call stutter stack light, you can actually just call it your function itself. That's how it's recursive. Okay, it's just when you think about it, it's sometimes hard to think, why do I have access to the function we're writing? Isn't that the point of the function? We're writing that function. Okay, so sometimes it's easier to think, okay, I'm actually using like a light version of the function. But when you write the code, you can just say stutter stack. Okay, does that make sense? Okay, in general, this is what like a recursive function generally looks like. Okay, you want to make the input a little smaller, make the recursive call, and then combine the recursive calls. Any questions? Okay. Let's quickly write this code up, okay? All right, let's quickly write this code up. So here, do you all have a code step-by-step account? Okay, you should make a code step-by-step account because it's a really nice way to code. And when you press submit, it will automatically run a bunch of tests for you. So it will check if your answer's right. Okay, cool. So let's write some pseudocode for this thing we write over here. Okay, so how should we get started? What code can we write over here? So let's do base case and a recursive case. Okay, what should our base case be? Yeah.
If s dot is empty. right?
Sure. Okay.
And then return s.
Yeah, sure. You don't have to return anything because our yeah, we're just modifying s.
Oh.
Yeah. So what you can do here is you can just say return semicolon. Okay. You can do that in a void function. That way you don't. It just immediately ends the function. Yeah. Oh, it's not on the screen. Oh, that's odd. Let's see. Do we see anything? Yes. Yes, we do. Okay. Cool. All right. So that's the base case. What would the recursive case look like? Okay, so yeah, remember our steps are we pop the first element out, so int top equal to s dot pop. Okay, so we pop the first element out. What's next? Yeah, we call the function, right? Here is where we call like stutter stack light. You can just call stutter stack itself, stutter stack s. Okay, so we can trust at this point we've fully stutter stacked s. What's next? Last. Push. So s dot push. And how many times do we push it? Twice. S dot push. Okay. Here's the cool thing about this website. Yay. Okay. Any questions? Okay, a couple things I want to know. First thing is Tyler, oftentimes during lecture, he writes this thing called an implicit base case. Right? Anyone remember what an implicit base case is? Yeah, an implicit base case will look something like this. If s is not empty, is empty. If s is not empty, then do this. If s is not empty, then do this, and then you wouldn't need this part, right? So here you don't explicitly have a base case, but it's implicit in that if s is empty, then you don't do anything. Okay. I personally prefer to write it this way because that makes it super clear that the recursion stops here. Okay, the recursion has to stop here. Now, so yeah, that's the thing called implicit base case. I prefer to write it explicitly as when it's empty, you stop. Other thing I want to know, some prefer to write their recursive function like this. Some they will do something like this. Okay, So think about what's happening right now. You pop, and then if it's empty, if it's not empty, then you continue stutter stacking. But if it is empty, then you don't make the recursive call. Okay? Anyone see any problems with this? Yes?
You pop it like in the beginning, like it could not be empty, like you'd actually have to call the function on that first one.
Yeah, exactly. Because if you do this, then if it's the empty stack, if we initially just pass in the empty stack, then that will cause a problem. Okay, so suppose, what if we take that advice and we just do this instead? So if it's empty, then don't do anything. Okay, now it works. Like if you run it, it works. But any other like style things you notice here? Yeah, it's a little redundant, right? You're saying if it's empty, and then you're checking if it's not empty, then you stutter stack. Notice what happens when you pass in any stack, right? It's gonna keep calling. The stack gets smaller and smaller, but when you only have one element left, you pop the top. You realize it is empty, so you don't make the recursive call. Okay. Notice that the recursion never ends in the base case, right? You'll always what happens is you always reach this point, you pop, it's empty, you skip the recursive call, then you push it back up. You never reach this base case unless you start off empty, right? Okay, now here's a really important concept. A recursive function should always end in a base case, okay? Okay, everyone say it with me. Recursion always ends in a base case. Recursion always ends in a base case, okay? So in this function, notice that the recursion doesn't end in the base case. So what's better is if we remove this part and just trust the recursion works and make it fall into the base case. Okay. That thing that we saw before, that was bad code. That's called arm's length recursion. If you see that on on a comment, that means you're essentially trying to avoid going into a base case by stopping a little beforehand. Okay. Does that make sense? Okay. Let's just hear that sound one more time. Yay, okay. Any questions? All right. I want to do one more example. Okay, this is a really fun example because we're going to write a parser. 20 minutes. We have barely under 20 minutes. We can do this. All right, so we're going to write a math parser. This, I personally feel, is way more interesting than any of the questions on this handout, okay? But, so let's just try it. This is on the level of something you might do on your assignment. And this is really relevant for some later assignments. You'll have to do something like this, okay? When I took the class, our final project was to write, it's basically code Excel, like code the program Excel. And one thing you had to do is you had to know how to like parse expressions like this, and you wouldn't write something like what we're doing, okay? So write a recursive function named evaluate, which accepts a string as a parameter, which is a fully parenthesized valid math expression, and evaluates the expression and returns an integer. So the idea is we pass in a string like this into the function, and then it returns 3 times 4, 12, 12 times 12 plus 4, 16, something like that, okay? Now, for simplicity, our expression will only contain positive single digits. So like you see in black over here, single digits. And we're only going to use the operators plus and times. Now, if you wanted to extend this, you can easily do it. Basically, just add more operators. Find a way to parse like digits, like numbers that are more than 1 digit. But because that's not really relevant to recursion, we're just not going to do that here. Your homework, or your challenge, if you choose to accept it, is to extend this functionality. Okay, you can build a really extensive parser just by doing this. Okay, cool. Now, for simplicity, we'll also assume that our expression is fully parenthesized, okay? And the reason for that is because I still never remember order of operations. They're annoying, so we're just not going to worry about them. What does fully parenthesized mean? It means like in a expression like this, between every operator that you see over here, like these are color coded, you'll always see parentheses around the 2 expressions that are being added or multiplied. Okay, so for example, here you see that because the 2 operators, this operator plus is acting on the 3 and the 1, we wrap it in parentheses. Same thing over here, right? Because this pink operator is acting on the 1 and this expression over here, we're going to wrap it in parentheses. All right, you won't see anywhere where you have to figure out what the order of operations are. Does that make sense? Okay. And then I won't go through this, but for the sake of simplicity, we're not going to use any of those. You might start to think, oh, wow, that's crazy. We're not going to use any loops, any ADTs, no string functions. I might cheat and I might use s dot substring, okay? But we're not going to use any parser. Realistically, if you are actually going to write a parser, you should use these functions. Like, don't try to limit yourself just to show off. But my goal is just to show you how powerful recursion is, okay? Okay, so just as a last thing, these are some valid expressions. You could have single digits. Notice that for 3 plus 4, you have to wrap that in parentheses, even if you don't need it. Right, this is just for simplicity. And then invalid expressions, you can see like the mistakes are highlighted in red. Okay, any questions? The bottom one, yeah. So the bottom one, notice if you trace through the colors, you'll see that the bottom one, you'll notice that let's see. Yeah, so like the green is acting on this thing and this thing over here, right? But then like we forgot to wrap this in like a parentheses to show, so we don't have to worry about order of operations. Right? If you notice here, you have to worry about, do you do the times first or the plus first? Okay, so just for simplicity, we're going to wrap everything in parentheses. So it's clear what order you do the parentheses, okay? Okay, let's do some whiteboard and some code. Can I get the projector up? All right, let's take a look at, actually, I don't think I have to move it up. Let's take a look at this expression we see over here, okay? What do you notice is self-similar about it? There's a self-similarity to this large expression. Yeah, sorry.
It's wrapped with parentheses.
Okay, so we see that this large expression it's wrapped with parentheses. What do you notice about the stuff inside the parentheses? Yeah.
There's only one operation in each level.
Okay, so there's one operation in each level, and then between the operator and the parentheses, what do you notice is true about this thing and this thing? Yes?
This might be wrong, but there's like an addition, and then multiplying those two additions.
Addition,
Because,
addition.
one-
Yeah, so what you notice is these are also expressions, right?
Oh, yeah.
Yeah, these are also expressions. Yeah, you're exactly right. You see like additions within them, but if you look at this expression as a whole, it's also an expression. Okay? So this whole thing is an expression, but what is an expression composed of? It's composed of, so this is an expression. This is an expression. And what, in addition to like these two smaller expressions, what else is in this large expression? Yeah.
In the smaller expressions of 1 plus 2.
Yeah. So within these expressions, there are like these smaller expressions as well, right? Yeah. And in addition to that, you also have like this plus sign, and you also have these. Okay. The key self-similar part you have to know here is that one large expression, a large expression, is the same as a parentheses, some operator, another parentheses, and two smaller expressions. Small expression, small. Okay? If we were writing a function, evaluate, which takes in the whole expression and outputs an answer, if we had access to evaluate light, how can we evaluate this entire expression? Yeah, go ahead.
You just figure out the two expressions and use the operation to answer.
Yeah, exactly, right? Because you have access to evaluate light, you can first try to find where the expressions are, and then call evaluate light on this one, call evaluate light on this one, and then just figure out what operation it is and just add them together, okay? So as part of our parser, what we're gonna do is we're gonna have to first, find the open parentheses, find the small expressions, find what the operator is, and then make sure you just call evaluate light on this one and this one. All right, we're going to call evaluate light. Let's use orange. Evaluate light on this one and evaluate light on this one. Okay, this will give you something like 3 times. This will give you something like 12, and this will give you something like 4. Knowing that, you can add them. Okay. See what the self-similarity is here. To evaluate the large expression, you have to evaluate the 2 smaller sub-expressions. Any questions at this point? Okay, if you were writing this as a code and you had access to evaluate light, how would you find where the expressions are? This is a little tricky. Okay, so parentheses, right? So like for example, you know that if this first parentheses belongs to the outer expression, when you see this parentheses, you know that that's the start of the inner expression. How do you find where the first small expression ends? One thing you could do is if you went to section last week, there's a problem where you can use like a stack. Try to make sure that they're balanced. When you finally see the one that balances this one, you know you're done. That's one thing you could do. Okay, unfortunately, we can't use stacks. We can't use loops. So unfortunately, it's not so easy to find these expressions, right? Any other ideas how we might approach this? Yes?
Just like use int variable to keep track of the level of the parentheses. So if you meet a left one, you just add 1. If you meet a right one, you just minus 1. So when the int variable is 0, you are doing with things at the same level. So if you meet an operation at level 0, it's gonna be the operation of this one.
Sure.
So between the whole expression is divided by the operation.
Okay. So you're saying use recursion to. This is gonna be recursive, right? No, just go through it and then. Oh, I see. So use a variable, go through it, and then try to figure out where it's balanced. Yeah, you could do that. Okay. You'd have to use a for loop for that, and I think that's a good way to go through it, try to find where the end of the expression is using a loop. Okay. We're not gonna use a loop here. Yeah, go ahead.
This could also be really long, but I remember we did an example lecture, like the palindrome example, where we track the outside and the inside. So maybe using a recursive kind of thing. So, I don't know.
Yeah, sure. Okay, yeah, I think that's a good idea as well, where we essentially track that inwards. Okay, yeah, I think that's a good idea. I think it's just really hard to find this part, right? This part's a little hard to find. Okay. Yeah, these are all really good ideas. If we didn't have the restrictions, we would totally. I think pretty much real parsers, they're implemented using the ways you explained. Okay. Unfortunately, we're gonna just use recursion over here. Okay. Now here's an idea. This function we're writing is a little complicated to think about. Let's write a function called int evaluate and consume. Okay, it's going to take a string by reference. Now you might ask, why do we take it by reference? What's going to happen is we're going to look at some sort of string, and what it's going to do is it's going to evaluate the first full expression it finds, and it's going to consume it. Okay, so what does that mean? Let's say, suppose we said evaluate and consume of, suppose we had 3. It doesn't have to take in a fully valid expression. We can give it this expression. 2 plus 3 plus 4 plus 1, and then plus 1. Okay, so notice that this is a valid expression. Let's see. Let me not use this example. Let me use this example. Okay. What this function is going to do is it's going to essentially find the first valid expression it finds, and it's just going to evaluate it. Okay. So for example, if we started here, what would the first valid expression we find be? 1 plus 2 parentheses, right? Yeah, this would be the first valid expression we find. We can't include anything here because that's part of the pink. So what it's going to do is it's going to find the first expression it finds, evaluate it, And then what's going to happen is, since we passed it by reference, we're just going to remove this part from the string. Okay? So we're going to write a function, evaluate and consume, which moves forward, consumes as much as it can, and then it evaluates the value of that. And it changes s so that it consumes the part it already had. Okay? Now, if you think about what's going to happen, if you keep repeating this, what is going to happen at the very end? You're going to have what? Yeah, so you'll definitely return an integer. What happens to this string? It's going to be empty at the very end, right? It's going to keep consuming until it doesn't have anything at the very end. Okay, so one thing we're going to do here is we're going to say if s dot is empty. So if our expression just doesn't have anything in it, what should we return? Let's just return 0, all right? All right, otherwise, how should we move it so it consumes the first expression it finds? We're almost out of time, so I want to move a little faster with this. To find the first expression that it finds, right? What you should do is you should first, one possibility that happens is you reach a digit, right? If you reach a single digit, so if you consider these expressions, what's the simplest kind of expression you can find? It's just one digit, right? So one thing that could happen is if you reach a single digit. If like the next thing is a single digit, so if s, the first is a single digit, there's a function called isDigit of s0. If it's a single digit, then how should you evaluate that? Yeah, just s0, turn it into an integer, right? Okay. Here's a clever way to turn something in a digit into an integer. You can just do return s0 minus, char d is equal to s0. Because we have to consume it, we're going to say s dot substring oops, s is equal to s dot substring 0, 1, 0. So we have to consume that digit, and then we can return d minus 0. Okay, so this turns it into a digit. Okay, this is just a clever C++ thing you do. You can turn a digit into a character into that digit. Okay, so let's see. What does this do? This consumes one character, that one single character. Otherwise, if it's just not one single character, then what should you do? Right, if it's not just one single character, then you should consume the first thing you find. Look at the operator, consume the next thing you find, move past the parentheses, and then add the two things you found. Okay, we're almost out of time, so I'm just going to quickly write this out. So let's see. We first start by moving past the parentheses. So s equals s dot. I think I have to do an s dot equals s dot substring 1 here to move past this. Moves past the first parentheses. S dot substring. Let's see. We start by moving past the parentheses. We find the first element, and then actually we do this here. My apologies. S dot substring 1 here. This moves past the open parentheses. Then we evaluate the first expression we find. So int expression 1 is equal to evaluate and consume. This looks at the very first expression it finds, and it consumes it. So s. Okay, after we consume that, what's the next character we find? That's the operator, right? So char operator is equal to S0. Okay. Then we can, we want to move past that again. So S dot substring 1. So this moves past the operator. After we move past that operator, we can look for like this in their expression again. So let's do int expression 2 is equal to evaluate and consume S. So that will evaluate the second operator, right? Oops, the second operator. Okay, then we're almost done. We just have to move past that one more time. S dot substr S equals S dot substr 1. So that will move us past that operator. Okay, and then now essentially you can just say, okay, you have expression 1, you have expression 2. You can either add or multiply them based on what the operator is. Does that make sense? Okay, I went through this a little fast, but I'll just do a. Oh, the whiteboard's not down. Great. Yeah, but essentially you can just add these two or multiply these two together, and that will give you your expression. Okay, I went through this a little fast. I'll send this as an email as about what the final solution, and then you can see what the solution looks like. Okay, the idea is we want to write a function which evaluates as much as it can, and then it consumes that amount. Does that make sense? Okay, any questions right now? Okay, sorry I went a little fast at the end. We're out of time, but thanks for coming. Here are handouts. Please take the solutions. Here's some solutions, and please also take some of the chocolate peanut butter cups.